This question tells us to use this substitution to show that these two integrals are in fact equivalent to one another, are in fact equal. And from there we have to determine the common value, or basically we have to evaluate at least one of these integrals. So, and also it says hence, so we're definitely going to need to use this equality at some stage. But first let's try and prove it. So we're given this integral from 0 to pi over 2 of cosine x over sine x plus cosine x. What can we do with this? Well, on its own, not a lot. So let's try using the substitution. Let's substitute, this is dx. Let's substitute in x equals to pi over 2 minus y. And then, just so we know, dx dy is going to be minus 1. Or rather, dx is equal to negative dy, if we want to think about it this way. So this is equal to what? Pi over 2. If x is equal to pi over 2, what's y going to equal to? It's going to be 0. What about if x equals to 0, then y is going to be pi over 2. Okay, so that looks a bit funny, but we can actually evaluate integrals this way. It's not too much of a problem. We then get cosine of pi over 2 minus y over sine pi over 2 minus y plus cosine pi over 2 minus y. Okay, good. And instead of dx, we get minus dy, right? And so now what we want to do is we want to show that this expression here is actually equivalent to this one up here. So that's how we're going to proceed. How do we do that? Well, we've got this minus dy here, but we've also got these integrals back to front. So we can actually use that to undo each other. Those can undo each other because you can flip the integral, flip the bounds, and it just changes the integral by negative 1. So that is, if I now write 0 to pi, I can now also write dy without having to have the minus sign. To clarify things a little bit more, let's just remember for a moment that I'll just use red. No, I won't. I'll use blue. Remember that if I have cosine of a negative argument, that's the same thing as the cosine of the positive argument. That is, the cosine function is symmetric around the y-axis. Whereas, if I have a negative argument for sine, I can pull the negative sign out the front, and I get negative, so sine of negative x is equal to negative sine of x, making sine what we call an odd function. So we're going to make use of both of these facts now, basically. So I'm going to write this as, this is the same thing as cosine, wrong color, cosine of y minus pi upon 2. Right? And I can do this because plus or minus 1 doesn't make a difference to the cosine function. Over negative sine of y minus pi upon 2 plus cosine of y minus pi upon 2. Again, I've just multiplied this by negative 1, but because I've done that, I've got to put a negative sign out the front. Sorry, this should be pi upon 2 here. Okay, now what can we say about cosine of y minus pi upon 2? What can I find out about cosine of y minus pi upon 2? Well, we're going to use our graphing calculator and see what we can find out. So I'm now on the graphing tab of Microsoft Mathematics. I'm going to enter a function y is equal to cosine of x, so this will be the first one we'll look at. And then the second one we're going to look at is going to be y is equal to cosine of x minus pi upon 2. And let's see what we get here. So we'll graph these. And this is what we see. So this is a bit small. Let's move it over a bit. Right. This is our cosine graph in blue. And we can see that when we've subtracted pi upon 2, we've moved everything to the left. Sorry, we moved everything right by pi upon 2. That is, we've shifted the phase. And now if you look at it, this no longer looks cosine graph, the one in green. It now looks a lot like a sine graph, and in fact it is the sine graph precisely. So this is equal to sine of y. As easy as that. What about sine of y minus pi upon 2? So we've got this function here, right? And we've got to be able to change that into something recognizable. So what about sine of y minus pi upon 2? Well, let's go back here. Looks at our equations again. Let's clear all of this. Reset graphing tab. There we go. And let's enter in some equations. So let's try y equals to sine of x. And in the one just below that, let's try y equals to sine of x minus pi upon 2. And see what we get. So again we graph. And again, this blue one is our sine graph. You can see here, this blue one is the sine graph. And when we've subtracted pi upon 2 from the argument, again we've moved everything to the right by pi upon 2 radians. So now if you look at this graph, the green one, it doesn't look like sine so much as it looks like an upside down cosine graph, or negative cosine. So actually this is equal to the negative cosine of y. So these two are going to be very useful, and you can derive them from your graphing calculator. So what is our next step going to be from here? This is equal to pi upon 2, 0. This one on the top is now, I'm now going to write it as sine of y over negative sine of this, of y minus pi upon 2 is going to be the same thing as negative cosine y, or just cosine y, plus, and again this is the same thing, sine y dy. So we've shown that this is actually equal to pi upon 2, 0, cosine x over sine x plus cosine x dx. But the key thing is here, right, x and y, they're just variables, they're letters. I can choose whichever letter I want. And in particular, there's no reason why this can't be x either. So therefore, pi upon 2, 0 of sine of x over cosine x plus sine x dx is equal to pi upon 2, 0 cosine x over sine x plus cosine x dx. So these two are in fact equal. So that deals with the first part of the question. Show that they're equal. Hence, determine the common value of the integral. So how are we going to determine the common value of the integral using this equation? Because it said hence, we're going to have to make use of this equation somehow. Well, maybe the integral itself from pi upon 2, 0 to pi upon 2 cosine x over cosine x plus sine x. This is going to be quite hard to integrate on its own. But what happens if I had two of them, right? Then this is the same thing as the integral of pi upon 2, 0 cosine x over sine x plus cosine x plus itself again, right? Pi upon 2, 0. Sorry if this gets a bit cramped. Can I move over a little bit? Yes, I can. Dx. Okay. But then I can turn one of these into sine, right? So this is the same thing as the integral pi upon 2, 0 cosine x over sine x plus cosine x dx plus the integral of pi upon 2, 0 sine x over sine x plus cosine x dx. And now, because these integrals have the same bounds and the same variable, and with respect to the same variable, I can actually combine them into one expression. This is the same thing as cosine x over sine x plus cosine x plus sine x over sine x plus cosine x dx. Now what am I going to do? Well, they've got the same denominator, so this is the same thing as pi upon 2, 0 cosine x plus sine x over sine x plus cosine x dx. And what do you know? These cancel out, right? So that just leaves us to integrate between 0 and pi upon 2, 1 dx. And so the answer for this one is just going to be x between pi over 2 and 0. And so the answer for that is pi upon 2. But what is this? This is actually 2 times our first integral, right? Cosine x over sine x plus sine x dx. So it's not our final answer. To get our final answer, our final answer, the integral from 0 to 2 pi of cosine x over sine x plus cosine x dx is equal to pi over 2 divided by 2 is equal to pi upon 4. And we are done.